give me the same energy. Now why do I say 6 eigenfunctions? Because the eigenfunction depends on the n, of course, right? Where does that come from? From the alphas, right? So if I choose two different values of n, if I change the n's, I change the alphas. If I change the alphas, I'm changing the eigenfunctions. Okay, so I'll have 6 different eigenfunctions for the same energy, 14 here, right? So just written here. So there are 6 different stationary states. Remember that from earlier sessions? A stationary state. That's a state that you get when the potential V does not depend on time. Okay? So stationary means doesn't move. Okay. Now, going back, reversing that sort of thinking, if the dimensions of your box, your A1, A2, A3, if they're all different, if it's a rectangular box, whatever, then you do not get degeneracy, right? And so that makes you suspicious that degeneracy might have something to do with symmetry. Right? We got this degeneracy because we made this rectangular box a cube. So we got a cube has all kinds of symmetries, and so you become suspicious that in quantum mechanics, degeneracy, meaning you have more than one eigenfunction with the same eigenvalue. Remember that? Okay, so you may get degeneracy due to symmetry. So remember that for the future, because symmetry in quantum mechanics, symmetry in physics, plays an incredibly important role, which is one of the reasons why I'll be taking you up to PhD 2 level in group theory, because group theory is all about symmetries. Right? It's the mathematics of symmetries. Right? Okay, so now changing the topic a little bit, this particular session does several things. One is it talks about, it gives a second solution to a STI, Schrödinger time-independent equation, and it introduces 2 concepts. One we've done already, degeneracy, and this second one, a new one, is called parity. And I'll get onto that in a minute. All right. Okay, so now let's go back to the 1D case. So instead of talking about a box, we're now back to just a region along one-dimensional line along the x-axis, say. So between minus a and plus a, let's say. All right. Now, so go back to the previous session, and you may remember that the wave function u. The solution to it, there were of 2 forms. It was either 1 over square root of a times sine n pi x over 2a, or 1 over square root of a cos n pi x over 2a. Right? Those were the 2 solutions to the one-dimensional case. Okay? Now, have a look at this. Are you familiar with the notion of an even or an odd function? Have you heard that from maybe high school calculus? A function is said to be even if it takes on the same value when you mirror flip it, like when you reflect it. So if u of minus x is the same as u of x, so like the mirror image kind of thing, if that's the case, that function, that u, is said to be, by definition, even. Okay? But if when you flip it, you make it minus, so you sort of go like that. So if u of minus x is minus u of x, that function by definition is said to be odd, an odd function. Okay? So that's the definition of an even function. That's the definition of an odd function, right? Well, so this evenness or oddness, when you're talking about a wave function, the evenness or the oddness is given a special name. It's called parity, right? So if I ask you what's the parity of a particular wave function, you would answer even or odd, depending on which it is. Right? So parity is just it's just evenness or oddness, but within the context of this, well, wave mechanics, right? So it's a technical word used within wave mechanics, but it just, all it does is just taking the idea of evenness or oddness of a function from mathematics. Right? That's all it is. But physicists, they're using their own term for it. They just call it parity, whereas the mathematicians would call it either evenness or oddness of functions. Same thing, right? Okay. Now, there's a bit of a side note here. You may notice it starts off fairly sparse and big letters for greater visibility. I mean, I was learning that trick for when I was, until very recently, filming in standard STD, standard definition. But this is now the second session that I've recorded in high definition. So I'm hoping these small letters here you can actually now see. In which case I may put more on the board, because I'm getting a little worried. As I go to higher and higher levels, there are going to be a lot more equations and a lot more deduction and logic, and it gets tougher. So I will need to put more on the board if possible. So I'm hoping the high definition may solve that problem. But I can't go too small, because then I'm back in the same problem again, right? You can't read the board because it's too small and it's too fuzzy. All right, anyway. So as I move from left to right on the board, it tends to get smaller because I'm becoming increasingly conscious. Oh, I'm running out of board. I have to finish this point, so I have to fit it in, so make things smaller. Anyway, right. Now, you may see here proof. So what's happening now is starting to get the physics is starting to sound a bit like pure mathematics, in the sense of theorem statement, proof. Now, if you have followed me right through the finite group theory, you'll be quite familiar with proofs and lemmas and theorem statements and so forth. So here's like the beginnings of one, where the physics is starting to sound like pure math, right? So let's talk about the notion of parity, and let's assume also that the potential V is even. It's an even function. Okay, so by definition, V of minus x is V of x. In other words, your potential is symmetric about the x-axis. Now that's true. Well, it was true in the one-dimensional case, right? Here's your x-axis and a and minus a, and the potential was just 0 over that range, and it was 0 at a and it was 0 at minus a. It was 0 at half a and it was 0 at minus half a, and so on. Right? It was symmetric. Okay, so if your potential is symmetric, then so long as you've got a non-degenerate stationary state, right? So stationary state, that's a wave function you get when your potential is time independent, right? Stationary, meaning it doesn't move, remember? Okay. And non-degenerate, that means for every solution, every your wave function you get as a solution from your STI, Schrödinger time independent equation, right? So for every wave function, you get a different eigenvalue, right? Non-degenerate. Okay. Then your wave function u will have even or odd parity. Right? So if you've got all these conditions satisfied, so your potential is symmetric, right? It's an even function. Your wave function is non-degenerate, stationary state, in other words your V doesn't change. You've got all these conditions met. If all that's true, then, that's the theorem statement, then your wave function U will have even or odd parity. Okay? So you can look on that as a kind of theorem statement. Now we give the proof, and I hope this comes out. It's getting a bit small, but it's a kind of test for high definition. And if it comes out fine, I'll be very happy. It means I can put more on the board in the future, because I need to, right? Either that I'll have to have many sessions when the math gets really dense. I'm worried about this. When I look at the higher level texts that I plan to teach at PhD level particularly, there are so many equations, like quantum field theory, just riddled with equations and so forth. So it worries me a little. All right. Okay, so here's the proof. Well, here's the statement of your STI, right? The Schrödinger time-independent equation. And instead of going u of x, we're putting in minus x. Okay? U minus x, u minus x. So we've just rewritten the STI. I'm not even going to bother saying what it is anymore. I'll just call it the STI, right? So we just rewrite the STI with u of x replaced by u of minus x. All right? Now, notice here, I've just got v of x. Well, that's because of this, right? I mean, it could have been v of minus x. Let's say you start that way, but then replace v of x. Also, I save a line. Okay? All right? Now, you're told that your eigenfunction, your wave function, is non-degenerate, right? So that means for the same eigenvalue, the same energy, in other words, your eigenfunction is for each eigenvalue there's one and only one eigenfunction. Okay, it's non-degenerate. It is not degenerate, right? So now that is your STI. Now except you've got u to the minus x here. So this function, whatever it is, u of minus x, for it to be, it must be the same, except for a constant. It has to be the same as just u of x. Right? It can't be different. If it were different, if this were not some constant times u of x, that means you'd have two eigenfunctions for the same e. And that, by definition, is degenerate. Right? So therefore, your u of minus x must be some constant times u of x. Right? Well, let's put in u of minus of x, right? Which is just x, of course, u of x. So u of minus of something is ku of minus x, right? Whatever this is here, you put here. But u of minus x is just k of x, so you get this k squared u of x. So k squared u of x is just u of x. So k squared is 1. Okay, k squared equals 1. And therefore k must be plus or minus 1. Now if k is plus or minus 1 from here, that means that u of minus x equals plus or minus u of x. That means that this eigenfunction, this wave function, this u, equals plus or minus u of x. In other words, the parity of this wave function, this eigenfunction, is odd or even. It has odd or even parity. Right? So there's the proof. That was the proof. That was the theorem statement, and from here downwards is the proof of the theorem. So quantum mechanics, well, physics, mathematical physics, is starting to look more and more like pure mathematics, and that's the intention. If you keep following me for years, you will speak pure mathematics and math physics equally fluently. That's the plan. Okay? Right, well, that's the end of the second session in high definition. I'm curious to see how this small writing comes out. It's a test. So till next time.